no conversation about acids and bases would be complete without water. Why? Because we're talking about all of this in water. What is water? Is it an acid? Is it a base? Is it nothing? Is it everything? Let's find out. All right, so let's look at a couple reactions that we've already looked at. We had HCl, aqueous, plus water goes to H3O plus. I almost wrote H plus just out of habit. H3O plus aqueous plus Cl minus aqueous. And then we also have the ammonia reaction we talked about. Ammonia reacts with water to form an equilibrium of NH4 plus and OH minus. Right, so there's two reactions using water. Let's look at our acid-base definitions. Acid is a proton donor. The hydrogen here gets dumped out of the Cl and over to the water. So this guy is an acid. And who accepts it, right? The water accepts it, so that makes the water the base. Right? How about in the case of ammonia? Ammonia, NH3 becomes NH4. How? Because water gives it a proton. Water goes from H2O to HO, right? And H plus left. All right, but what does that make water? That makes water the acid because he's giving away an H plus, and that makes NH3 the base. So here we have water. Is water the acid or is water the base? You're like, I don't know. And the answer is it's both, and it's neither. It changes. It's not set. Just like you behave very different probably in front of your parents as you do in front of your peers, right? You're hanging out with your friends doing stuff, you're not behaving in the same way that you behave when you're behaving around your parents. Right? And that's normal because how you behave depends on who you're hanging out with, right? You hang out with good people, you're going to probably be doing good things. You hang out with the not so good people, you're going to be doing not so good things. So hang out with the good people. Anyway, so that's what water does. If water's hanging out with somebody who's like, I am a great acid, yeah! It's like, sure, I'll be a base, that's fine, no problem. But if somebody's like, oh, I'm a base, base, then water will be, sure, I'll be an acid. Yeah, here, have my hydrogen, no problem. Whatever you need, okay? It's very accommodating. Okay? And we call that behavior amphoteric, which means it can act as either an acid or a base depending on the circumstance. Water is by far the most common one, but there's lots of amphoteric things out there. We'll see a few as we go through the class, but we're going to talk about water for now. And here's the funny one. Water is amphoteric even to itself. If we write the reaction H2O liquid plus, I'm going to use a different color here, H2O liquid, we can have that react where the red water gives up its proton and the black water accepts the proton, and you end up with H3O plus and OH minus. This is a perfectly valid reaction to write. Remember, we can write whatever reaction we want as long as it's balanced. Whether it occurs is a different thing, okay? But this is a perfectly valid one to write, and it does occur. We know it occurs. There's all sorts of studies on it. And so this reaction does happen. And since it's in equilibrium, it also has an equilibrium constant. We're going to write K for this guy. KEQ is going to be, what is it? The concentration of H3O plus, concentration of OH minus, and we don't have to write the waters there because they're both liquid, and so they don't come into the equilibrium expression. So if there's an equilibrium expression, there's also an equilibrium constant, and this one is equal to 1 times 10 to the minus 14th. Now, in this class, we're going to treat that 1 times 10 to the minus 14th as a constant under all circumstances. It's not. It changes with temperature. We talked about that at the end of the equilibrium chapter, that equilibrium constants do change with temperature. But we're not going to cover that. Okay, we're just going to assume that this is a constant. We're going to treat it as a constant. We're even going to treat it as an exact constant, even though it's not. So we're going to treat as exact, even though it isn't. Why? Because it makes our life easier. Okay, that's why. We're going to just make our life a little bit easier by treating it as an exact constant. So if it is an equilibrium constant and it's this one that we're going to find that we're going to use all sorts of places, let's give it its own name. Why? Just for like acids. If I say Ka, you're like, oh, HA goes to H plus plus A minus, I know that. If I say Kw, you say, hey, that's my water autoionization. Auto right? Doing it by itself, ionization, turning into ions. Water plus water make these two ions, H3O plus and OH minus. Okay, that's the water autoionization constant, and it is 1 times 10 to the minus 14th. Treated as exact for this class, although it's not technically exact. Remember, this is the same thing as writing H plus and OH minus. You don't have to write the H3O plus, and you'll find that most of the times I use that second reaction because, again, it's just slightly easier to write H plus than it is to write H3O plus. So we're going to use that all the time. And remember, if it's a constant, when we multiply those things, it's always going to be equal to 1 times 10 to the minus 14th. What does that mean? It means if I add something that has a lot of H plus in it, right, and that H plus concentration gets bigger and bigger, in order to multiply it and still get the same number, my OH minus has to go down in proper ratio to what my H plus goes up. So as my acidity increases, right, I become more acidic by having more H plus, my OH goes down. And the opposite would be true. As my OH goes up, my acid has to go down. And it's always going to be the same. Now, let's just talk about this in an ice table. Well, if we just start with pure water, right, and then we react it, right, we've got water, water, we've got none of this and none of that, right, no H3O plus and no OH minus. As it reacts, right, what are we going to do? We're going to form X of this and X of this. We don't care about these guys because they don't appear on our equilibrium expression. And so what we actually find is if we wrote out the ice table completely, we'd just get X times X. Right? So pure water, if we solved that, we'd get 1 times 10 to the minus 14th equals X times X. We get X is equal to 1 times 10 to the minus 7th molar. And maybe that is familiar to you, depending on what you covered in your previous chemistry classes. But that's the concentration of H plus or OH minus in pure water. And how that number come about is just from an equilibrium calculation, just from an ice table equilibrium calculation, starting with pure water, using the equilibrium constant of water, the autoionization of water, and so we get the 1 times 10 to the minus 7th molar. And that's the concentration of H plus and the concentration of OH minus in pure water. Technically at 25 degrees Celsius, but we're going to treat it as constant. So that's where that comes from if you've ever seen it before. And we're going to use this quite a lot to calculate H plus from OH or OH from H plus as we need to. So let's do that. Okay, it's often important to know one from the other. So if we know our OH minus and we're looking to find our H plus, we can just write that expression that Kw is equal to H plus times OH minus. And we can just solve that. What are we solving for? We're solving for the H plus, so we're going to divide both sides by OH minus. Cancel, cancel. We get that my concentration of H plus is just going to be Kw over my concentration of OH minus, which is 1 times 10 to the minus 14th over 1.0 times 10 to the minus 5th. And if we do that math, we get 1.0 times 10 to the minus 9th molar. Okay? So that would be my H plus concentration given my OH minus concentration. You'll notice a few things that might be a little familiar from the equilibrium chapter. As I was writing these out as part of the equation, I didn't put units on them because technically we're dividing by that reference concentration to get that to cancel out, so there's no units on K. However, when I wrote my final answer, I made sure to have that molar. If you put a molar on there as you were working, I wouldn't have a problem with that, but technically you don't need to because in this case we are dividing by those reference concentrations. The other thing I want you to pay attention to is significant figures. Since we're treating Kw as exact, in this equation there's only two things with significant figures, the H plus and the OH minus. So whatever significant figures you have for your H plus is also the significant figures you have for your OH minus. So I had two significant figures in my OH minus, which means I had two significant figures in my H plus. Let's go ahead and do the next one. We've got H plus and we're trying to find OH minus. If you do the same thing and your screen doesn't go crazy, which it just did. I'm not sure what my screen just did. There we go. If we solve for OH minus, it's just going to be Kw over H plus. or 1 times 10 to the minus 14th over 3.82 times 10 to the minus 2 from this problem. And if you plug that in a calculator, you get 2.62 times 10 to the minus 13 molar as your OH minus concentration. We got to look at our significant figures. We had 3 significant figures down here, so we have 3 significant figures over here. So that's how we can find OH minus from H plus, or we can find H plus from OH minus just by using that Kw expression. Kw is H plus concentration times OH minus concentration. So this is your turn. Find your OH minus concentration in a system where H plus is 2.28 times 10 to the minus 9th molar. Okay, so what did you come up with? Well, hopefully you're like, hey, I just need to find my OH minus concentration, which is going to be Kw over my H plus. You plug in the 1 times 10 to the minus 14th here. You plug in your 2.28 times 10 to the minus 9th here. You plug that into your calculator. And if you think about just the exponents, 10 to the minus 14th divided by 10 to the minus 9th, that should give you something around 10 to the minus 5th or so. So you can pretty well just eliminate that guy. You can pretty well eliminate that guy, and maybe it'll give you one or the other, but to get 1 times 10 to the minus 7th, you would have had to divide by 1 times 10 to the minus 7th. So you can eliminate that guy without ever plugging this into your calculator. But if you do plug it into your calculator, you get 4.39 times 10 to the minus 6, 3 significant figures on that concentration, because I had 3 significant figures on this concentration. All right. So imagine several hundred years ago, you're trying to write a book on all this kind of stuff. And you've got these concentrations of 3.55 times 10 to the minus 5th molar. How are you going to typeset that when you actually have to typeset actual characters one by one? That's really hard to do. And so one way to get around that typesetting need was to take a log. And so people defined a pH scale. And the primary reason, as far as I'm aware, I could be wrong on this, the primary reason of the pH scale was just to make writing these numbers a bit easier. It was much easier to write these pHs, as you'll see in a moment, than it is to write the scientific notation. So people defined this thing called the power of hydrogen, pH, and it's just 3 bars is a definition. Negative log of the concentration of H plus, and that is the log base 10. You'll never see me write the 10 again. That's the first and last time you'll probably ever see me write that. But it is the log base 10 of the concentration of H plus. So if I wanted to calculate pH for H plus is 1.0 times 10 to the minus 5th, I would just take the negative log of 1.0 times 10 to the minus 5th. Again, we leave units out because we are dividing by reference concentrations. Why? Because you can't take the log of a unit. It's not possible. You always have to make sure your units cancel out somehow when you take a log. So we are dividing by that reference concentration. And what do you get? You get 5.00. You're like, why those zeros there? My calculator just gives me 5. We'll get to that in a sec. How about this? We're going to double our H plus concentrations. We're going to take it from 1 times 10 to the minus 5th to 2 times 10 to the minus 5th. What's that going to do to our pH? If you go ahead and plug that negative log of 2.0 times 10 to the minus 5th into your calculator, you get a whopping 4.69. So what do we find? As we increase our H plus concentration, right, we doubled it, our pH went down. And so we can see that the more H plus we have, the lower our pH is. So it is an indicator of H plus concentration directly, right? There's a mathematical relationship with it, but it's something to think about too. As that pH gets down, it just means you have more and more H plus. Since we know H plus and OH minus are related by Kw, it means I have less and less OH minus. All right, now we're going to calculate the pH for the OH minus, 4.7 times 10 to the minus 9th. And you're like, ooh, you didn't give us an expression for calculating the pH from an OH minus. Okay? So few different ways to do this. We're going to start with this way, is we're going to use Kw equals H plus times OH minus to solve for H plus, which is going to be 1 times 10 to the minus 14th Kw over 4.7 times 10 to the minus 9th molar, and that's going to be 2.13 times 10 to the minus 6. Keeping an extra sig fig since this is an intermediate calculation, and we're going to take the negative log of 2.13 times 10 to the minus 6, and we get a pH of 5.67. Okay. Now, why all these decimals? Why am I getting 2 digits after the decimal in everything, or 3 significant figures, it kind of looks like, right? Here, you're like, I had 2 significant figures, but it looks like, Professor Clements, that you're getting 3 significant figures. But that's actually not the case. It turns out when you do logs, what does this 5 mean? That 5 just means 10 to the minus 5th. And the 10 to the minus 5th, because we took the negative log, that's why that negative's there. That 10 to the minus 5th, that's just the exponent in scientific notation. That's not a significant figure. That's just my exponent. So it turns out when you take something that's a log, it's only the digits after the decimal that are actually the significant figures. And so my 2 significant figures here actually get 2 digits after the decimal here. And that's how we do our pH significant figures. The significant figures in our concentration become digits after the decimal in pH. If we had a pH that was 11, so we had a H plus concentration that was 1.0 times 10 to the minus 11th molar, you took the log of that, your calculator would tell you 11, but you'd actually put 11.00. So it would look like 4 significant figures if you didn't know it was a pH, but since we know that only the digits after the decimal are the significant ones, we just have 2 significant figures. If I talk too fast, just play it again. It's a lovely thing about videos. I can talk as fast as I want, and I love to talk fast. All right. Down here, 2 significant figures, 2 digits after the decimal. 2 significant figures, 2 digits after the decimal. Oop, you didn't see my underlines. 2 digits after the decimal. If we had a concentration that was 1.00 times 10 to the minus 8th, my pH would be 8.000. If I had 1 times 10 to the minus 8th, my pH would be 8.0. Okay, so I should put my molars there. So that's how we do it. Number of significant figures becomes number of digits after the decimal. But what if we want to do it the other way? What if we had a pH and we wanted to know the H plus? So we look at our definition. Our definition of pH is pH equals negative log of the concentration of H plus. Let's solve that for the concentration of H plus. First thing we're going to do is multiply both sides by a negative. So we get negative pH is equal to the log of the concentration of H plus. Now we have to undo log. We can't just divide by log, because log's a function, not a number. So you can't divide by a function. You have to undo the function. The function that undoes log is power 10. And so now we have power 10 to both sides, and we have this expression that my H plus equals 10 to the minus pH. And we can solve for H plus concentration. If I had a pH equals 9.00, my H plus would be 10 to the minus 9.00, or if you wrote it out in scientific notation, 1 times 10 to the minus 9th. Now, what about significant figures here? Well, it turns out that when we went forward, we went from significant figures in concentration to digits after the decimal in pH. When we go backwards, what do? We do digits after the decimal in pH to significant figures in concentration. We actually have to write that with 2 significant figures. That's 1.0 times 10 to the minus 9th molar, because we had 2 digits after the decimal in our pH. Those 2 digits after the decimal became 2 significant figures in our pH. So it works backwards and forwards. Significant figures in concentration becomes digits after decimal in pH. Digits after the decimal in pH become significant figures in concentration. It's the same backwards and forwards. So your turn. We're going to find the OH minus in a system where the pH is 2.33. And you're like, doesn't sound quite familiar, but you know how to do it. So go ahead. OH minus in a system where the pH is 2.33. What'd you come up with? Well, pH is 2.33. You know that's a fairly low pH, so you know you're going to have a fairly high concentration of H+. So I'm going to guess off the top of my head that it's probably not either one of those. But let's go ahead and do the math to figure it out. We've got that our H+ is 10 to the minus pH, or 10 to the minus 2.33. And for some reason, I didn't write that number down, so let me go ahead and put that into my calculator. 10 to the minus 2.33. And by the way, when you're putting this into your calculator, you do have to use the 10 to the power function. You can't quite see that. It's the second log. Okay, you can't use the built-in scientific notation, the EE, or times 10 to the x, because it doesn't deal with decimals. So if you had a 3.5 in there, your calculator wouldn't do that. So 10 to the minus 2.33, that is going to be 4.68 times 10 to the minus third molar H plus, but we were asked to find the OH minus, and so we do KW over H plus is OH minus, and I'm just going to put that in my calculator, and that's 1 times 10 to the minus 14th divided by that previous answer, and I get 2.13 times 10 to the minus 12th as my OH minus concentration. So the thing I said at the beginning, I was thinking backwards. Okay, I was thinking H plus concentration, right? So hopefully you were confused when I said that, and I apologize. I try not to say confusing things in my video, but I'm human, and I don't want to have to record all 30 minutes or 20 minutes of this again. Okay, so when I said X, I was thinking H plus. I wasn't thinking OH minus, but we're solving for the OH minus here. So in a system with a low pH, we know it's going to have a high H plus concentration. It's going to have a low OH minus concentration. Now, what about our significant figures here? Because these two are equivalent answers, just significant figures. We look back. Our pH had 2 digits after the decimal, which means we only get 2 significant figures in our answer, or 2.1 times 10 to the minus 12th molar as our answer, and so we get D there. So again, apologies for that mistake in my thinking, but you can see I wrote this problem. I've practiced this problem. I've solved this problem many times in my career. But it's really easy to make that mistake. It's really easy to not pay attention and to think what you're thinking as opposed to really paying attention to the question. So I don't mind making mistakes here and there. I don't like to, but I don't mind because it really teaches you that even people who do this on a regular basis can make little errors. And what I did is I got to my answer and I said, that doesn't make sense in light of what I said earlier. So either this is wrong or what I said earlier was wrong, and I had to think about it. I said, oh, that was the mistake I made. I didn't get to this answer and be like, no, I already crossed those out, so obviously I don't know what I'm doing. No, I said, okay, I've got two things that are not consistent with one another. One of them must be wrong. It's possible that both of them are wrong too. But one of them must be wrong, so let me figure out where did I possibly go wrong? And I figured out that was my logic at the beginning that went wrong rather than my calculations. All right. Beware of your calculator. I know a good chunk of you use this calculator. I love this calculator. It is essentially indestructible, and it's $10. And I kid you not, I've never found light that's dim enough that this little solar panel doesn't work. Okay, so if you're ever out in the wilderness and you need to make some calculations to, I don't know, do something, then you can use this guy because it'll work day and night. It's really great. So go ahead and try this. I'm not going to make you pause. I'm not going to force you to pause using the play pause it, but I'm going to give you a chance to pause. What is OH minus? It's H plus is 2.25 times 10 to the minus 6 molar. So go ahead and pause and try that one. No, really, I did pause a little there. That meant for you to pause. Pause the video. Okay, so now you actually paused. And what did your calculator tell you? Did your calculator tell you 0.000000004? I love this calculator, it's great, but there's some things it doesn't do well. And one of the things it doesn't do well is knowing when to switch from decimal notation to scientific notation. Casio, other manufacturers' calculators, they do that just fine. But Texas Instruments, like, no, I can still write a decimal there. I'm going to write that decimal. But what's the problem here? Do we only have one significant figure in our answer? And the answer is no, we don't have just one significant figure in our answer. We need to actually get more significant figures out of this number. So I'm going to go ahead and put this in my calculator so you can see what I'm doing. 1 times 10 to the minus 14th divided by 2.25 times 10 to the minus 6. I hope you tried that one. And by default, you're going to get this little 0.00004, and that's not what I want. I need to get, what do I get? 3 significant figures. Now, I've seen students do this, and they write 4.00 times 10 to the minus 9th molar. They counted their zeros, and they just put a couple zeros at the end. Do you know those are zeros? Your calculator didn't tell them to you as zero, so you don't know they're zero. You can't just make up zeros. I mean, imagine if you could do that. Your bank account, I have $10. Let me just put a few zeros after that. Look, I'm a millionaire. You can't just make up zeros. Okay, so what do you have to do? You have to tell your calculator, okay, look, I know you can display this as a decimal, but just for my sake, can you please display it in scientific notation? And how you do that is you press the second key, then you press this little one that says DRG, sci-eng in purple or blue above that. And it says, do you want flow, psi, or eng? And you want psi. You want everything in scientific notation. You hit psi, you hit enter, and all of a sudden, look at that. It's 4.44444 times 10 to the minus ninth. And so you get that as your answer. Whoa, that's a horrible 9. Let's fix that. There we go, 10 to the minus ninth molar. And so you get those actual significant figures. Now, just beware. Now, whenever you type something in, I typed in the number 20, and it's trying to tell me that is 2.0 times 10 to the first. Everything will be in scientific notation. So I quite frequently will go back to second, DRG, and then change it back to flow, which stands for floating point, which means it automatically tries to determine the best thing. But it's really useful if you don't really want to count digits to be able to switch back and forth. I switch on my calculator all the time while I'm making calculations, constantly back and forth, back and forth, back and forth, because I think sometimes it's useful to have scientific notation. Sometimes it's useful to have the decimal notation. So be aware of that. Okay, so here are yours. Given a pH is 5.925, what is the OH minus concentration? Okay. What'd you do? Well, you said, I know this. I know that H plus is 10 to the minus pH. And so that's going to be 10 to the minus 5.925. And what's that going to be? It's going to be, again, numbers for some reason I did not write down. 10 to the minus 5.925 gives me, again, 0.000189. So I'm going to tell my calculator, go scientific notation, please. 1.19 times 10 to the minus 6 molar. But that's my H plus concentration. I want OH minus concentration. And yes, for those of you who've done this before, we're going to get to POH and doing it simpler in a little bit. OK, OH is going to be KW over H plus. So I'm going to put in my 1 times 10 to the minus 14th. And then divide by that number, and we get 8.414 times 10 to the minus 9th molar. I put a lot of significant digits there on purpose so I can think about it later. 3 digits after the decimal is going to give me 3 significant figures, and I get 8.41 times 10 to the minus 9th molar, and we get D. Right? And you could have done that relatively logically as well. Again, just trying to figure out what do we expect. Is OH going to be high or low? Since we have a low pH, it's very acidic. We're going to expect a lower OH minus concentration, less than 10 to the minus 7th molar, because that was what neutral was. And then we can figure out the significant figures. But it's better to know how to calculate that. All right. Another one. Oh, another one. Given that my OH minus is 4.92 times 10 to the 4th, what is my pH? All right. Getting the hang of these. H plus first. H plus equals KW over OH minus. And then we're going to take the negative log of that. So what is my H plus concentration? It's going to be 1 times 10 to the minus 14th divided by my 4.92 times 10 to the minus 4th. And that's going to be 2.03 times 10 to the minus 11th molar is my H plus concentration. I take the log of that, and I get 10.691965, whatever. So what am I going to do? Look at my significant figures. 3 significant figures should become 3 digits after the decimal. And it didn't put the 1 there originally. I just added that. 10.6919, which rounds to 10.692. All right. So there we go. Digits after the decimal, pH. Or sorry, significant figures becomes digits after decimal and pH, and back and forth. All right. Now, it turns out that once we figured out we could take the P, the power of H, it turns out it's very useful for anything that's written in scientific notation to be able to take the P of that, the power, the negative log. And so it turns out we have all sorts of definitions that POH is the negative log of the concentration of OH minus. The pKa is the negative log of my Ka value. pKw is the negative log of my Kw value. So if you see all of these here, you're just going to figure out, take whatever that P thing is, and you're going to put that in the negative log, okay? If it's OH, you can put OH minus concentration. If it's KW, you're going to put KW in there. And notice that these are not subscripted or superscripted, so they're just written out. They're really easy to write. You don't have to write the subscripts anymore, whereas you do when you write Ka, Kw, those should be properly subscripted, or OH minus should be properly superscripted. So they are a little bit easier to work with than working with scientific notation. So be aware of those, and also write backwards that if we wanted to know Kw, that's going to be 10 to the minus pKw just by solving that expression. I realized as I was going through all these examples that there is a little chart I forgot to cover when we were talking about the definition of pH, and that one is right there, is what is the pH scale? Well, if you remember, the concentration of H plus in pure water was 1 times 10 to the minus 7th. You take the negative log of that, you get a pH of 7. So neutral water is considered to be a pH of 7. Anything below that, as H plus concentration increases, pH goes down. So anything below 7 is considered acidic because it has more H plus than it does OH minus. Anything greater than 7 is considered basic because it has less H plus than OH minus, or conversely, more OH minus than H plus. And you'll notice there's a big list of acidic things, a very small list of basic things, because in our daily life we run across a lot more stuff that's acidic than we do stuff that's basic. Why? Think of Drano. You guys know what Drano is? It's used for cleaning drains, right? So you've got hair clogs, all kinds of stuff in there. You pour some Drano in, it dissolves all of that and allows your drain to get clear. So what does basic stuff do? It's great at dissolving organic matter. What are you made up of? Oh yeah, organic matter. So that's why we don't run across highly basic things very often, because it tends to dissolve us, and none of us like being dissolved. Whereas acids, I mean, look at our gastric juices, right? Our gastric juices are up here at the top of that pyramid. We have very acidic stomachs. And so our body is designed to be able to handle quite an acidic situation in some cases, especially with regards to stuff we ingest. A lot of the foods we ingest are very, very acidic. Soft drinks, 2 to 4 pH, limes, 1.8 to 2.0 pH. And that's fine because our body is designed for mostly acidic things. So just be aware of that. pH of 7 is considered neutral. Anything below that, acidic. Anything above that is basic. Thanks for listening to this talk about the equilibrium constant and its use in finding H plus and OH minus concentrations, and our definitions of pH and P everything else. Thanks.